Good morning, everyone. We're working on some review. We did it on the first unit, a little bit of function notation, and then we're going to introduce some like real-world type word problems that we can use to model our model and linear equations. And then tomorrow there'll be more word problems as we get ready to wrap up this unit for the test next week. So first thing, function notation. We've been working with slope-intercept form, which we remember is y equals mx plus b. Actually, I have that on slide. Never mind. So we know that it's y equals mx plus b. What we're going to do is we're going to introduce this function notation again, which changes y. It's considered, this form here, where it's more linear equation, what we're looking at, we're going to change it to a function. So we're going to use the name f of x. Is what we call it. We show it as f and then the x in parentheses, and then it's still our equation mx plus b. So it's the same as y equals mx plus b. What it's telling us, though, is we're going to be able to plug in for x, whatever's inside the parentheses. So if we see an example, it's like f of 3. Then what we're doing is wherever we see x in our equation, we're going to plug in a 3 and calculate the equation out to figure out what the value is. Does that make sense? Okay. So for some examples, we have our equation f of x equals 2/3 x plus 9. So we're told to evaluate it at these 4 different numbers. So all we're doing, it's just like we said, it's just like y equals mx plus b. We have our equation. It's not really worrisome. In our example here, it's 2/3 x plus 9. All we're doing is we're plugging the different numbers you see in the parentheses for x. So for our first example, f of -12, we're going to have 2/3 times -12 plus 9. So if you remember, this is really 12/1 or -12/1. So we're multiplying fractions, we just multiply across the top, multiply across the bottom, and then simplify if we can. Or if you remember as well, we can kind of simplify them beforehand by cross-canceling. I can divide both 3 and -12 by 3. That'll become a 1. This becomes -4. So now when I'm multiplying across, I just have 2 times -4 and then 1 times 1. So this is really -8 plus 9, which equals 1. So then we know f of -12. So when the function is 12, when x is 12, the value is -1. Make sense? Same thing with the next one. We have 2/3 times 3 plus 9. Again, the 3's will cancel, so I end up with 2 plus 9. That's going to be 11. -9. So now we have f of 9. So now I have 2/3x. So it's actually 2/3 times 9 plus 9. So this becomes, think of it as 9/1. So I can multiply across. That's 18/3, which is 6, plus 9. That equals 15. And then our last one, f of 6. So again, it's 2/3 times 6 plus 9. That cancel. This becomes 2. So it's 4 plus 9, or 13. Does that make sense? Does everybody see that? Are there any questions on how we got to where that was? Okay, so here's some examples for you to try. The function is f of x equals 5x minus 25. I gave you 6 values that I need you to plug in. Go through Edpuzzle. Go through, solve your work, enter your answers into Edpuzzle, and as always, come back and check and see how you did. Okay, so our equations: 5 times 9 minus 25, 45 minus 25, 20. 5 times 4 minus 25, 20 minus 25, 5. 4 times, or f is 0, so it's 5 times 0 minus 25. So I end up with -25 there. 7 is 5 times 7. minus 25, that's going to be 10. 25 times 20 minus 25 becomes 100. Minus 25 is 75. And then the last one, 5 times negative 6 minus 25, negative 30 minus 25, or negative 55. Everybody see that? It's pretty simple. It's pretty easy to do. Like I said, there's not a lot to it, not a whole lot to this as we're going through it. So, moving on now. Here, I'm just asking you to rewrite the equations in function notation. Again, I think it's pretty simple to do. Enter your answers in the end puzzle, then come back and see how you did. Okay, remember, when you're asked to rewrite an equation in function notation, all you're doing is you're replacing y with that f of x. So rather than y, we're going to have f of x equals 1 over 2x plus 9. So that's all you're doing for all of them. So you should f of x equals 4x plus 9, f of x equals 1/2 x plus 9, f of x equals 5x minus 1. Here becomes f of x equals 2 over 3x minus 7. F of x equals negative 7 over 4x minus 10. And the last one, f of x equals 3x plus 100. Again, fairly simple, fairly straightforward. Shouldn't have been any problem. Now we get into where we can start modeling these equations and modeling problems with function notation for real world examples. So here we are. We can do, like I said, we can model a lot of these real world situations as linear equations depending on what we're looking at. So here's an example where we have a cable company charges $40 for installation and then $60 per month. It reduces its installation fee to attract new customers. It reduces its installation fee to $5. And we're asked to create functions to show each scenario in function notation, then graph each function and compare the graphs. So the one thing I always like to point out in word problems when we're dealing with linear equations, whenever you see the terms per something, so here we have per month, that is your slope. That identifies slope. The word per IDs the slope. So I see $60 per month. I know right away my slope is going to be, or my equation is going to have 60x in it. If you want to do month, even better, because we can kind of switch variables out now. Once we start working with real world stuff, it doesn't always have to be x, y, and x, especially using function notation. But here, my first equation is going to be f of x equals, like I say, slope is 60x. The installation fee, that's the cost up front. That's going to be my y-intercept. That's where we're starting. Before I even do anything with my cable thing, I have to pay $40 out. So when x is 0, I've already paid $40. Does that make sense? So this is what they usually charge. If we kind of change it up, they've changed their installation fee to $5. Again, they didn't change their rate. So it's still $60 per month, so 60x. And then we're going to call that plus 5. Real world examples, though, the problem with those is we kind of have to start working with different scales on our graphs to kind of fit them in. So we kind of have to start working that way. I'm going to make every single one of my lines worth a 5. So I'm going to start here. For my first equation, I'm going to have 40. So I'm going to go 8 boxes. 1, 2, 3, 7, 8. So here's my 40 right there. My slope is 60 over 1. So what I have to do for that now is I actually have to go over, I have to go up 60. So I have to go up 12 spots and then over 1. My y-intercept's by 5. So let's just say that. Y-intercept's by 5. My x-intercept is still by 1. So here I got to go up 12. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 is right here. It's really not working for me on this map today. Start over here with some good numbers. So I got 1, 2, 3, 4, 5. So there is x, y-intercept. Well, that's up 6, sorry, over 1. So there's my that. So my equation is going to look like this. My scale could have been a little bit better, but this is the best I can do. So here's my first equation. Second one, they've started at 5. So here we go. Again, I'm going up 12, 7. So that puts me kind of here. Lines aren't great. So there we go. That really didn't work well. See if I can do this line better. We'll call that 1. So there's my 1. See how many lines I got way over here. Sorry, give me a minute here. Oops, we got 1, 2, 3, 4, 5. All right, so I can make each one of those 2. That's how we're going to do it. It'll look better this way. No, that's not going to work. Make each one 4. 1, 2, 3, 4, 5, 6. We'll call that 10. Again, now I have to go up 15 from there. So over 1, go up 15. So there's our first line, close enough. Second line is going to start here, kind of. Again, go up 15. The second line is going to kind of look like this. So there's our 2 lines. Still not the best, but you get the idea. We have to kind of figure out the right scale to put our graphs in. So when we compare the 2 graphs, the only difference is the y-intercepts changed because that's where we went from $40 of insulation to $50. We have the same slopes because the $60 didn't change. So if we remember back to Friday, we actually have parallel lines because the slope didn't change. Does that make sense? Okay, another example. The average price of a movie ticket in the United States went from 80 cents from 1980 to 2000, is modeled by the function f of x equals 10 cents x plus 275, where x is the number of years since 1980. They want us to graph the function and identify domain and range. So here what I'm going to do is each one of my lines here is 0.1, if that helps. Each one of my y-axes, I will do, I guess, let's call it 25 cents. Does that make sense? Actually, let's make that 0.12. How about 0.05? That'll work. That's my slope. 0.05 for the y. So we're going to graph the function. So again, we're graphing y-intercept first, which is $2.75. That should be, can't be 0.5. It has to be 0.1. Like I said before, my scale is going to work better at 0.1 because I don't have enough lines. So this is 0.1. So I have to go up like 27.5. So we got 1, 2, 3, 4, 5, 6. So that's my y-intercept right there. My slope is then up 0.1 to the right, 1. So I guess that's going to put me way over here somewhere. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So up 0.1 is going to put me here. So it's a very, very slow and steady movement. Actually, let's change that to 1. Again, this is so hard when you start dealing with these craziness of your scales. I'm going to call this here as 1. So I go 0.1 over 1, I go another up 0.1 over another 1. So kind of here's the increase of your equation. So we've identified that we're asking our domain and range. This is really actually 1980 is what I should say. So the domain and range is really going to be 0 to, you want to call it 20. So domain here for our example here is we're starting at a point where we're starting in 1980, so we're not really going below 0. So my domain is going to be 0 is going to be less than x, which is going to be less than 20 because we're really only worried about 2000. And then the range is going to be from 2.75 because we're starting with our y-intercept at 0 is 2.75 is less than y, which is less than, I'm going to call it positive infinity because I don't know how far it's going to go. So then they ask us to find the value of x so that f of x equals 455. Well, now we're just going to solve our equation. We're going to set up our equation as 4.55 equals 0.10x plus 2.75. Now we're just going to solve for x. We're going to subtract 2.75 from both sides. So I end up with, this is 1.80 equals 0.10x. We divide both sides by 0.1. We end up with x equals 18. So it's 18 years from 1980 is when the price of a movie ticket went to $4.55 on average in the United States, I guess. Does that make sense? It would be out here somewhere. Does that make sense? Everybody see that? Okay, here's one for you to try. Don't be confused. It's d of x where they just changed it because we were talking about distance. So they made the function d of x rather than f of x. So take a look at the equation, graph the function, figure out a good, decent scale. I know it's kind of small and tight, so you don't have to use 1 for 1 to work it out. But try that, and then find out how far they're going to travel, how long it will take them to travel 50 miles, and then 15 miles, and then how far will they travel in 4. Okay, so we have our d of x equals 10x, sorry. All right, so to graph our function, I don't know what scale you used. What I'm going to do is I'm going to make every 5 bars on the bottom 1. So that's 1. Make this 2. Make that 3, and then on, so on. I should go up to 4 because that's where I need to be. 1, 2, 3, 4, 5. Okay. Then up the side, let's do every 2 is 10, I guess. Actually, let's do every 4 is 10. That'll be better. One, 2, 3, 4. So this is 10. 1, 2, 3, 4. This is 20. That would be 30. 1, 2, yep. 40. 50. Okay. So I have my scale set up. They're asking me to define the function. So when x is 0, y is 0. So that's my slope. There's no y-intercept, remember? Because we could rewrite this as plus 0. So there's nothing there. So we're starting at the origin. Slope is 10 for every 1, so I go from here, that's 1, so that's my slope. So I can kind of do this for my lines. Goes off like that. So, domain. Again, I've already said it starts at 0. We're going from 0 to 0, so my domain is 0 is less than x, less than positive infinity. We can travel forever. Range, again, 0, less than y, less than positive infinity. We can be infinite amount of miles away. Does that make sense? Okay. So how long will it take to travel 15 miles? Well, if we look at our graph, 15 is kind of right here. So we kind of go here. I should be at 15, 1.5, 1.5 hours. The other thing I could do is I could plug in 15 miles equals 10 miles times x and divide both sides by 10 to solve that. I get x equals 1.5 hours. Make sense? Same thing on the other side. How far do they travel in 4 hours? Well, that's just 10 times 4. So d of 4 equals 10 times 4. So d equals 4 hours is 40 miles. That makes sense to everyone. Okay. Another example here. What we're showing here now is we're going to show two equations to try to help us solve a problem. So here are the number of hours of daylight in Austin, Texas during the month of March, per mile by the function 0.03x plus 11.5, where x is the day of the month. Graph the function daylight and identify the domain and range. So I'm just going to arbitrarily call this here my y-intercept. That's 11.55. My slope is 0.03 for every one. So if I call every line 0.03, that puts my slope here, here, here. I'm going to draw those lines in as best I can. This is my equation. The domain and range again. The domain equals 11.5. Sorry, domain is 0. My mistake. Because I'm starting with like 0 time, let's say. Domain is 0, less than x. I'm going to say less than or equal to 365 because we're only talking 365 days in a year. Does that make sense to everyone? Now that's what we're looking at. The range of our domain of our x, it's a yearly thing, so I can only go to 365. Range again is going to be, 11.55. Because that's the number of hours, the y-intercept kind of. So it's 11.55 less than x. I want to say less than 24 because the best they can do is have 24 hours of sunlight. I don't know how high we go, but it can't be any more than 24. So the second question was to graph the number of hours of darkness that can be modeled by the function dx equals 24 minus L of x. So here it gets a little trickier because what we're going to do here now is they're telling me my function d of x equals 24 minus L of x, which I already know is this. So I'm just going to plug this part of my equation in. So it's minus 0.03x plus 11.5. So what I need to do is kind of distribute the negative sign through. So it's minus 0.03x minus 11.55. So when I work this out, what I end up with is negative 0.03x plus 12.45. That's the number of hours of darkness we have. Does that make sense? So again, here I go up to kind of what I call these 0.3. So I am 0.9 away, so I go up 30 of them. Which worked out perfectly. So that's 12.45. That's my y-intercept for my darkness equation. And again, now it's down. Sorry, that's where I want to be. Now it's down 0.03. So this is my equation for that. When I draw that line in, we notice that they cross. So again, the domain and range is the same. It's 12.45 greater than x. So range here should be 12.45 greater than x greater than 0. Domain again is 0 and 365 for days. So what they're asking is where do the points of graphs intersect? What does that mean? Well, that's going to be the point where the daylight amount of daylight and darkness are exactly the same. Does that make sense? That's where they're the same? Okay. So here's another example for you to try. A little easier than the one I just did, hopefully. Again, graph the functions, try to figure out what's happening. They then give you your second function to try to figure out what it is. We're selling pretzels. We're trying to figure out our profit. So try to graph it out. Give yourself a few minutes. Come back and check and see how we did, and I will walk you through the solution. Okay, again, we're looking at the cost to make pretzels every day, done with the function. This should be plus 75, so C of X equals, so C of X equals negative 0.5X plus 75. Sorry about that, I didn't realize the typo before you started. So that's my equation, so I have to kind of come up with a scale again. Again, I'm gonna do every 2 bars is 1. And then I guess I'm gonna try every I don't know. What are we gonna do? Let's do everyone is 5, I guess. Since every 2 bars is 5. So if I do every 2 bars of 5, that makes that 15, which that is my y-intercept. That's gonna be my 75. This should be equal, not negative, so it's positive. So now my slope is 0.5x, so it's going up half a point. So it's going up very, very little. So as I kind of do this, I'm gonna have a point here, another point here, let's say here. So it's going up very slowly from my y-intercept point. So we'll just call that it. Does that make sense? Okay. So we graphed our cost function. They also told us that each pretzel sells for $3. So we're going to start at 0 here because I haven't sold any pretzels. So this is going up 3. So my first one should be here. Second one should be about 6, which should be about here. So again, this kind of goes up slowly this way. And it's eventually going to cross. So it should have crossed way out here somewhere. Not the best graph. So the profit here now is the difference between those two. So we can kind of figure out how many pretzels do we need to sell. Well, it's going to be this point out here, whatever that value is. I don't know from the graph because my scale is kind of wonky. But algebraically, to break even, I have to have my cost of the pretzels I sold. The sales from pretzels is 3x, has to equal 0.5x plus 75. So I kind of move some stuff around. I'll subtract 0.5x from both sides. And I end up with 2.5x equals 75. When divided by 2.5, x equals 30. So when I sell 30 pretzels, which again should be way off my chart, I'll break even and have a profit. So I think that was kind of confusing. I apologize for that. I'll try to do a better job tomorrow as we start getting into more of the deep part of the word problems. But I just kind of wanted to get you used to seeing function notation not always having to be f of x, because we have a c of x here, we have an r of x here. The last problem had d's of x. So just know that that's a different way to do y equals mx plus b. We can use the function notation, and then we're able to evaluate based on whatever's inside the parentheses. And have a good night. I will talk to everybody tomorrow, and enjoy your day.